right?
Yes, sir. Yes.
Yeah, this actually it's been long been done, and we don't do it because it's a very mature field and all. So if you remember, instead of the earthquakes, I showed you this sort of like snake-like wave, right? The sheer horizontal wave that for the moths. That's actually a very, very a good way of doing sensing. It's like quartz crystal microbalance, because when you have anything attached to the surface, it's like a loading onto the wave, right?
Yeah.
That, and because of the mass loading, just like AFM, right? If you say functionalize the AFM tip, and because AFM tips vibrate as well, so if you got immobilization of your biomolecules onto your AFM tip, then you have mass loading that causes a shift in the resonant frequency, and that shift can tell you, right, the amount of the mass there is on there, down to I think even femtogram or attograms. So yeah, so what you have to do is just do so for example antibody immobilization or something like that onto the same way, just like the FM tips, you can do it onto the chips. And you can combine that with driving flow to do microfluidics, and to overcome diffusion limitations by driving flow, so that you drive these biomolecules to the surface so that they bind more quickly, and then you can detect them through the resonance frequency shift, like what I mentioned before. So it's actually, there's a lot. You just have to Google SAW, or surface acoustic wave sensing, and there are tons and tons of papers on this.
Okay, sir. Thank you.
I see Professor Padmanabhan is online and having a question. Padmanabhan, sir, you can.
Yeah, am I audible?
Yes.
Okay. Professor Leslie, you is an exciting area. It's completely new, I guess. Really exciting. And so you've been talking about many kinds of materials, and your work on HKUST1, I mean, whatever, that's a three-dimensional material, three-dimensional morph, at least. So an exfoliation cannot happen there. Exfoliation cannot be, but okay, maybe small. I mean, it forms into the sizes of the particles, may be very small, nano sizes. It can break up that way. Yeah. But if you take my question, there are two questions, small questions. So one thing is that after you are doing the sonochemical treatment of HKUST, did you take a powder XRD of the material and find out whether it really matches with the real HKUST? Because of course, mostly it must be really comparable to the bulk material, suggesting that the structure is really retained. My second question is, suppose you take a two-dimensional morph. I mean, I could not say morph, it's a coordination polymers, two-dimensional, where the two-dimensional materials pack up into crystals by hydrogen bonding. Mm-hmm. So if you break up, sonochemistry can really break up, and delamination can happen, delamination can happen. But if you have a two-dimensional material fragmented, or rather the exfoliated one, do they fold up and then form a kind of a nanotubes? I mean, that will be very difficult to find out whether it's a, when one layer is, like for example, graphene, if it's exfoliated, it can just form a, fold up and form a nanotube. I mean, I don't know whether it has been reported at least, but then graphene and nanotube, carbon nanotube, you take a graphene and then fold up and you can have a form. You can have a nanotube. Similarly, if you exfoliate such a two-dimensional material, for example, MOS2, if you take it up, and can they fold up and then form a nanotube? I hope you got it, actually, my question.
Okay, so let me answer the first question first. That's the easy part.
Okay.
With the HCAS, here it's actually HCAS. We did post-synthesis confirmation. We did FTIR. We did TGA and things like that. So we know it's HCAS. The
Okay.
powder XRD I actually showed you. It's HCAS, but it's a lot more oriented.
It's okay, because the PXRE will be broad because breaks up into nano because the line broadening will be there. I mean that peak broadening, so it'll be very. But if you take an FTIR, is okay. FTIR and then confirm that will be fine.
Yeah.
Okay.
That's when we did that centrifugation to do the crystallization of the copper and BTC. In the case where we nebulized, we didn't get HCAS, and this is why we got a different structure. We couldn't call it HCAS anymore because HCAS has this is well-known structure. So it's a different. In this case, it's the same precursors, copper and BTC, but we get a completely different structure itself. And this is like almost a 2D or quasi 2D kind of morph. You see it's not rods, but it's actually a bit more flat compared to its lateral dimension. So almost like swords. So that's the answer to your first question. The second question is interesting. We haven't done exfoliation of morphs. It's not that simple to do in a sense because yeah.
I know because that's a. I mean, I don't think it's a weird question, but then I'm just thinking of that one. Nanotube formation cannot happen because you're always creating the disturbance there. So for forming a tube, you need to have a kind of a very slow process. So
Yes.
and you are always creating turbulence there, disturbance there. So it cannot fall up into a tube.
Maybe. I mean, we haven't seen it, but well, I never say no to everything. So watch this space. We're trying actually to do different types of exfoliation, not with moss, but a similar type of material. I think more so we get defects, like what I was showing you. You can create defect structures rather than manipulate their morphology and conformation. I mean, we never see the rolling up with the semiconducting materials, the 2D materials. But there, I guess people are more interested in large flakes rather than these rolls, I suppose.
Okay, thank you very much. It's an exciting area. So I really enjoyed your talk, I would say.
Thank you.
You're welcome.
Professor Yo, in connection with what Professor Padmanabhan asked, like when you apply sound waves, you do see that you are actually changing the morph arrangement. And is it time dependent? Like, can you do it like switch on, switch off so that you can bring back the morph into the original state? Or is it like you turn it on and then it goes all the way and then you completely change it?
I don't think it's reversible, if that's what you
I was
mean.
wondering if we can like do it switch on, switch off, and then maybe increase the pore size and then decrease. It can be useful in some selective.
The pore size, I've never seen it go the other way. I've been, again, we've never really tried, but maybe if we don't, or at least we didn't examine it too carefully. So we measured it after, like for example here, after 1 hour, we saw pore expansion. I don't know what happens if we waited and left it be. Would it shrink again? I guess different morphs might behave differently. So the more unstable morphs might shrink back. In fact, mill, I think mill is known to swell, right? So maybe that's something we can probably look at if you're interested. to see over time whether they go back. But I guess it's more relaxation than reversibility. But once you cross that barrier, you start breaking bonds and it becomes irreversible, I think.
Yeah, no, I was thinking of like using them for for example, like selective catalysis. Like you can let in a particular size substrate when you turn it on, and then when you turn it off, it closes, so there is no more release.
Maybe the more elastic morphs, the linkers which are a bit more elastic, like nil, probably might do something. I don't. Good question. Maybe it's something we can look at a bit more.
I have another question about the the sound waves that you make. I think maybe we can call it Leslie waves. You said they are not surface or bulk. They are like mixed.
Yeah.
So do you think does it matter like if you have them confined to only surface waves? Is it going to
Sorry,
affect?
I understand the question.
No.
Is it?
Yeah, if you can just confine them to the surface wave. I don't know if it can be done. Does it matter?
It is still a half a surface wave. All right. So we call it surface reflected both ways because if I call it Leslie waves, people stone me for heresy. But if you look at this is what it is, right? So if you look at the surface acoustic, a pure surface acoustic wave, this is on the top of where the same surface as the electrodes are, those finger-like electrodes. You see the surface wave, or that earthquake, right? And you flip at the bottom, you almost see no energy, right? So everything's localized on this surface. If you look at the hybrid wave, it's actually still in some ways a surface wave on one side, but because it leaks all its energy, it's like a bulk wave throughout the thickness. So it's still confined on the surface, right? It's still in the chip itself. It's just that it goes throughout the chip. It's not now. Of course, when it go once sound waves, right, they go into they diffract into the media they are in contact with anyway. So if you have liquid and all, it will leak the energy out and it becomes a bulk wave in the liquid or air, right? So that we have no control over because once it goes out into the whatever media it's coupled to, then it becomes a bulk wave. But on the chip itself, it maintains its mode, right? So whether that's why it's not a surface wave, neither is a pure bulk wave. It's it looked really strange, so we just called it this hybrid wave. But I don't know whether that answers your question because I wasn't exactly sure that or what you were trying to get at.
I think yeah, that's fine. I got it. No, I have another additional question regarding this. How safe these waves are to handle in, like, for example, in the laboratory? Do you need any special requirement or setup to?
No, you can't even hear them because they're 10 megahertz. You can,
I'm talking about a long-term exposure to the.
Oh no, because like I said, your mobile phone has 4 or 5 of these devices. It's safe. There's little radiation that's harmful. It's a RF frequency, radio frequency.
Thank you. I think we have a couple of other questions.
Dr. Naveen, is there a time for a short question?
Yes, sir, you can go ahead.
Okay. What's the ideal frequency you can use for delaminating 2D material for a MOS2 or even other 2D morph materials? Ideal frequency, approximately.
The ideal frequency. Well, we didn't really study the effects of frequency, but we were doing it at 10 megahertz. We did at 30 megahertz to I guess where frequency comes into play is this, right? So the higher your frequency, the shorter your penetration depth, right? So basically, higher frequencies travel a lot shorter distances, right? As you know. So if I go, say, at 1 gigahertz, if I have this liquid, it's not going to do very much. It can do something near the surface, right? So I want to match that penetration depth with the bulk, my characteristic length scale of my liquid or the sample coming in. So for us, it was at 10 megahertz.
Okay, thank you, Dr. Naveen. Okay, thank you.
Hello, Professor. It's very interesting to see how just this acoustic waves can transform the material. So I just have one question. Can we generalize that these waves can target only the weak interactions? Because mostly what is happening is exfoliation or breaking of some weak bonds, right?
That's not entirely true, because if you look at the well, it depends what you mean by weak or strong, right? But we can break we can split water, and
That's
that's
what.
not.
So we can target even covalent bonds.
Yeah. Why, I don't know, right? Because I do all these calculations, and like, to break a covalent bond, right? It's you need a lot of energy. I don't know where that energy is coming from.
That's what. It's really very impressive.
Yeah, so there must be some non-linear interactions going on, that, up conversion of energy or something like that. We're still trying to think about this, but it's not easy to study, I suppose. So we haven't got any answers to that. But the short answer is, we can actually, we do see the breaking of those bonds, the strong bonds.
Thank you.
Any more questions? Um, Thank you, sir, for enlightening us with your wonderful session and sharing your expertise and insight. Um, on behalf of Department of Chemistry and our entire Amrita family, I would like to extend my sincere gratitude to thank you for sparing your time and gracing the occasion.
Thank you very much. Hopefully we'll see you in person, all of you in person sometime.
Yes, sir.
Take care.
Thank you, sir. Now it's time for the lunch break. The lunch for all the guests of honor is arranged at Anugraha Hall. The session will resume at sharp 2 p.m. I request all the audience to join here by 2 p.m.
First, and
S9 students, please assemble in front of the stage.
ഫോട്ടോ എടുക്കാം മിസ് പോകുമ്പോ.
മോളെ കഴുത്തലല്ല
ഇതെവിടെ വെക്കുന്നു? ഞങ്ങളിപ്പോ പോകും. എടാ ഒന്നുകൂടെ, എനിക്ക് മനസ്സിലായില്ല. ശരി. അതിലൊട്ടും കൊള്ളത്തില്ല. ഞാൻ ഒരെണ്ണം എടുത്തിട്ട് ഇല്ല, എന്റെ നല്ലൊരെണ്ണം കിട്ടട്ടെ. അത് സാരമില്ല. കിട്ടിയോ? കേറി നിന്ന് ഇവിടെ എടുക്ക്. ആക്ഷൻ ആയി.
എങ്ങനെ നിക്കണ്ട ഇങ്ങനെ മതി. ഞാൻ വരുന്നില്ലേ? എസ്ക്യൂ അവിടെ അവിടെ നോക്കി സംസാരിക്കും. എന്തേലും വന്നോടാ?
എടാ, ഒന്ന് പോടാ.
ഹലോ,
ഒന്ന് പോ.
നീ നേരത്തെ രണ്ടെണ്ണം എടുത്തില്ലടി. ഇവിടോട്ട് അറിയിക്കും. നീ മതിയോ? കിട്ടിയോടാ? ഇല്ലടാ.
മിസ്റ്റർ ഗോപാൽ. ഗോപാൽ. ഗോപാലകൃഷ്ണ പൈ. എടാ മതി, പെട്ടെന്ന് എനിക്ക് പോയി കഴിക്കണം.
It's not with okay, I think I should be here. If you didn't see me, you tell me only. No, I'm very short. You can see me, right? Stay up. Stay there. Stay there. Better. Stay up. You can see me. Yeah. Preferably. Okay.
ഇതാണോ നല്ലത് അതാണോ നല്ലത് ഇതാണോ അവിടാണോ നല്ലത് ഏതാണോ നല്ലത് കറക്റ്റ് ആയിട്ടാണോ ഈ സൈഡിൽ നിന്നാണോ ആ സൈഡിൽ നിന്നാണോ ദേഹം വേണ്ട ബോഡി വേണ്ട പകുതി മതി ഇവിടോട്ട് പിടിച്ചാൽ മതിയോ ഓക്കെ ഇതേ പിടിക്കണോ അതോ താത്ത് വെക്കണോ ആ അങ്ങോട്ട് നോക്കിയാൽ മതിയോ
Hocam,
Buyurun hocam.
birazdan Rektor Hoca'yla görüşeceğim.
Tamam.
Var mı aklınızda bir şey söylemek istediğiniz?
Ben her şeyi söyledim neredeyse. Ayaküstü. Gittim. Hallettik. Maskot var ama uzun mu sizin görüşmeniz?
Uzun.
Nasıl görüşeceksiniz?
Kısa. Ben kapıda şöyle bir söyledim. Beklersen hocam dedi, bir görüşürüz dedi. Şu YÖK'ü ben ziyaret etmiştim ya, onunla ilgili
Yani
bilgi vereceğim.
Aynen.
Çünkü dönüşte bir konuşuruz demişti hocam.
Benim ayrı oldu dün akşam. Netim alanında otelli oldu. İlkay'a gidiyorum, otelli oldu.
Ayrı oldu mu? Tamam hocam.
Görenlerinizi aldınız mı hocam? Görenlerini açtım size.
Ben işte bilgisayarı biraz sonra.
Benim hocam bizim son yani bunu yapabilirsiniz. Buyurun hocam. İyiyim hocam. Buyur tabii ki her zaman hocam size. Buyurun hocam. Harika. Evet hocam. Evet hocam, isterseniz bunları yazışabilirsiniz de hani bizim konaklama şeyimiz yok diyerekten, desteğimiz yok ama Tömer'den Türkçe öğrenebilir. İnönü. Malatya. Peki, sizin kürsüye değil mi hocam? Doktoraya gelecek. Buyursunlar, çok mutlu oluruz. Gelsin. Endonezya öncelikli ülkelerimizden. Sizi bağlayıcı bir şey yok hocam. Hani sizi kötü hissettirecek bir durum yok. Hocam anlaşırsınız mutlaka. Yani mutlaka anlaşılıyor. Bende de Filistinli bir öğrenci var şu anda. Öğreniyorlar Türkçe. Tömer çok güzel öğretiyor hocam. Ama bizim üniversitemizin öğrencisi olacak. Bizim Tömer'imize gidecek bir yıl hocam. Endonezyalıların Türkçe öğreniyorlar hocam. Böyle bir şeyimiz var bizim. Verdiğimiz bir imkan var. Değil hocam, değil. Türkçe sınava girecek. Türkçe sınava girip gelecek. Yapar hocam, yani siz de anlaşırsınız bence. Sıkıntı olmaz. Bir şey olursa zaten biz destek oluruz buradan hocam. Yine her şekilde. Tamam hocam. Hocam işte dediğim gibi yurt vermiyoruz, bursumuz yok ama zaten böyle kendi hesabına gelen çok öğrenci oluyor hocam. Güzel de oluyor. Bir de belki kendi bursu vardır. TİKA'da, evet evet hocam, ya YTB'den alır ya TİKA'dan burs alır, zaten alıyordur hocam, alır yani. Onlar kendi başlarına hallediyorlar hocam. Yine bir şey olursa mutlaka arayın hocam, her zaman buradayız. Görüşmek üzere hocam, sağ olun, hoşçakalın. Neydi bunun ismi? Meltem Hoca.
Dr. Sevinch, can you hear me? Sevinch, can you hear me?
Yes, I can hear you. Can you hear me?
Yes, yes. I think we will start in 5 minutes. So we have
Okay,
people
okay. We
coming
will
into
start
the
in
room.
5 minutes. We
Okay. So
are
there, yeah, there will be an introduction for like 1 or 2 minutes, and then you can start with the talk.
okay.
Thank you.
Now coming to the final session of this day, I would like to invite Dr. Naveen V. Kulkarni, Associate Professor, Department of Chemistry, to introduce Dr. Sevinç Kurbanglu, Ankara University, Faculty of Pharmacy, Department of Analytical Chemistry, Turkey.
Dr. Sevinç Kurbanglu, welcome to the ICAMSC 2023. It's a pleasure to introduce you to the audience. Dr. Sevinç Kurbanglu is currently an associate professor at Ankara University, Faculty of Pharmacy, Department of Analytical Chemistry in Turkey. She received her PhD degree in analytical chemistry from Faculty of Pharmacy, Ankara University, and carried out her postdoctoral studies with Professor Friedrich Scheller at Potsdam University, Germany. She has published over 80 manuscripts in the journals of international reputation and over 25 book chapters. She recently has received Biosensor Early Career Women Award. Her research interests include biosensors, biological and chemical nanosensors, electrochemical assay for pharmaceutical compounds, and electrochemical sensors. Today, Dr. Sevinç would be delivering a talk on immobilization platforms for electrochemical enzyme-based biosensors and their applications. Dr. Sevinç, welcome to the ICA MSc 2023. The forum is all yours. Thank you.
Ma'am, you're not audible.
Okay. Hello, everyone. Hello from Ankara. Before starting, I would like to thank to Professor Naveen for this kind invitation. I will talk about today some parts of my research area. It is about enzyme-based biosensor, actually. Before starting, I would like to say that I hope this conference will be very beneficial for the every participants. And here is my outline. Firstly, I will give you brief information about what is sensor, biosensors, history of biosensors, enzyme-based biosensors, some immobilization methods, electrochemical nanobiosensors. Then I will give some results from our studies about electrochemical enzymatic biosensors. As some of you know, sensors are the devices or systems translate the information from the main domain into an output signal in order to offer the selective sensors for the analyte that can be measured. And sensors are the analytical devices that selectively and reversibly respond to the amount or the activity of a chemical agent. Actually, as a human, we are all sensors. We have 6 sensing elements. So we can also assemble ourselves as a sensor also. And according to IUPAC, sensor defining as a device that transforms chemical information ranging from the concentration of a specific sample component to total composition analysis into an analytically useful signal. The chemical information mentioned above may originate from a chemical reaction of the analyte or from a physical property of this system investigated. So in this paragraph, actually, there are many important keywords that we should take into consideration when we are working with the biosensors. First one, total composition of analysis is important. The chemical properties of the analyte is important. Also, the physical property of the system is important. These are actually the components of the biosensor. You should know the property of your analyte. And according to that analyte, you can select your biocomponent. And according to physical property, you should choose the transducer. And biosensors are the devices that enable rapid analysis of the most detection and monitoring of biological and chemical agents. And biosensor area combines biological, chemical, physical sciences together. And when we look at the elements of a biosensor can be based on nucleic acid cells, antibodies, enzymes. These are the biocomponents that can be used in the biosensors. And depending on the physical properties, depending on what you are going to analyze, you can use different transducers, electrodes. You can modify the surface of the electrode with nanoparticles. You can use microfluidics, etc. And you can also use different kind of samples. They can be cells, human biological fluids, food samples, environmental samples. These are the main analytes for the biosensors. And after these reactions, we can follow the output with the electronic systems, and we can generate biosensing responses. And in this talk, I mainly will talk about enzymes, enzyme-based biosensors and electrochemical methods that we are conducting. And when we look at the biological compounds-based sensors, means biosensors, they can be immunosensors or enzymatic sensors or microbial sensors, DNA sensors, and optosensors. These are the 5 different biosensor types, depending on the biocatalysis based ones. Their names are different depending on the biocomponent that we are using. And in this talk, I want to give a special slide for the father of biosensors, Professor Clark. The term biosensor was introduced by Clark and early in the 19th, and he monitored the amount of blood with an electrode during a surgery, and that is actually the introduction of the biosensor word to the science. And after this discovery, the first potentiometric biosensor to detect urea was conducted. Then there are different types of biosensors were also came to the place. When we look at the enzyme biosensors, enzymes are the main components are the proteins, and they have different amino acids that can play important roles in the metabolism that can found in living organisms. Proteins are macromolecules containing long chain of amino acids consisting of thousands of amino acids. And maybe you are familiar with enzymes. They are actually biological catalyzers. They are speeding up the biochemical reactions. And without enzyme, this barrier is really high. Activation energy needed to take this barrier. But with enzyme, activation energy decreases. So we can have the reactions easily in the presence of enzymes, we may say like that. So enzymes have some active sites that substrate can bind to these enzymes, and enzyme substrate complexes occurred. Then the enzymes can again regenerate from here, and the products are formed. So this is really important that you can use the enzyme several times. This is the important idea of the enzyme-based biosensor. As the enzymatic reaction completed, the product release and the active site turns into its original state. So you can again use the enzymes more than one time, we may say like that. And this reaction is depending on Locke and Kay model. Emil Fischer offered this Locke and Kay model, fit the enzyme and substrate complex to each other. The induced fit model was offered by Daniel Koshland, suggesting that the enzyme is inducted to undergo a structural rearrangement upon substrate binding due to the change in the shape of the active sites that is facilitating the reaction, enzymatic reaction. So there are three types of enzyme-based biosensor. In the first generation, second generation, and third generation, we may say. In the first generation, we apply a voltage during the electrochemical process, and we can directly measure the substrate product change, and we can induce oxygen oxidation of the hydrogen peroxide. We may follow this. In the second generation, we can put a mediator. These mediator can be also osmium complexes or other complexes that we can use in these studies. And in the third generation, we directly wire the electrode surface with the enzyme, and we directly follow the electron transfer from the enzyme to the transducer to the electrode surface. So why we are using electrochemistry in enzyme-based biosensors? You can also use some spectrophotometrical methods also. Enzyme-based biosensors generally used in electrochemistry. In nanobio devices, electrochemical methods are generally used actually, such as amperometry, voltammetry, potentiometry. Actually, we are taking advantages of the easy usage and directly following the enzymatic activity with the amperometry or CV. And we can directly follow the electrochemistry of the substrate or the product, not the enzyme, but the substrate can be electroactive or the product can be electroactive. We are following these information. And electrochemical nanobiosensors can also be prepared by modifying the transducer surface with several nanomaterials. We are also taking advantages of these nanomaterials by they can enhance the substrate or product's electrochemical responses. So we can prepare nanobiosensors in this case. And with the technology, we can use also screen printed electrodes, which is on you have in a small surface working electrode, counter electrode, reference electrode. And so miniaturization is really important, and we are taking care of these technology with the enzyme-based biosensor and electrochemistry. We are combining all of them. And enzymes are really fragile materials, biocomponents, and it is really difficult to work with them actually. And they are natively unstable. They can be easily inhibited, and they only work well on a natural substrate and under physiological conditions. And that's why immobilization term is coming, and this immobilization is really important. It refers to restricted movement or make it unable to move. So we are trying to immobilize the enzyme actually on the surface of the transducer. Then we want it to be active when we want, not freely move or not be fragile. So that's why the term immobilization enzyme is really, really important. And it gives also us repeatability, and continuously we can follow the enzymatic activity by immobilizing the enzymes. By immobilizing, the enzymes can be removed from the medium at the end of the reaction, and we can clean with the buffer just. Then we can again use it. So it gives us repeatability, not just using one time, we can use more time. And the immobilized enzymes have resistance to environmental conditions like pH, temperature can change, but as they are immobilized, as they are protected, they are more resistant to environmental conditions. And they are more stable compared to natural enzymes. and they can reveal higher activity after immobilization compared to free enzymes. And there can be degradation of the enzyme by itself decreases after immobilization. So there are 5 different types of immobilization methods. And covalent binding, you can use covalent binding agents. I will show examples about these immobilization methods. There can be adsorption, there can be cross-linking, and you can also encapsulate your enzyme on the surface, or enzymes can also be entrapped. And we are generally using redox enzymes as we are following the electrochemical properties of the substrate or the product. Here you may see the sucrose. Invertase is the enzyme, and it converts fructose to glucose. You can follow the glucose response. And we are also we can also use glucose oxidase. In this case, you can use oxygen loss or peroxide formation in the system. We are taking advantages of this. And cholesterol oxidase, again, it can be used. These oxidase enzyme, redox enzyme, are generally used in enzymatic electrochemical enzyme-based biosensors. So I want to give you examples from our work. In this work, we use invertase enzyme and by entrapment method. How we do that? We coat the surface of the electrode with a polymer. We use novel polymer that was synthesized by physical chemistry laboratories, and we just put the monomer and enzyme together in the solution. Then when we start the polymerization, enzymes are also entrapped in the polymerization step on the surface of the electrode. So by this case, we can prepare an entrapped invertase enzyme, and we follow the change in the substrate, the sucrose to glucose. We follow these reaction. And in another one, we also used we also performed pH stability, temperature stability of this enzyme-based biosensor, and we are using several times the same biosensor. And with a number of assays, you may see here, 50 days we made these, and it is showing this stability also. It's very important for us. And also shelf life, as we put this biosensor in the fridge, and we are just measuring and then keeping in the fridge, again measuring and keeping in the fridge. The shelf life is also important for us, and we are reporting these results. In another example, I want to show you immobilization of glucose oxidase, this time by covalent binding. For covalent binding, you need a cross-linking agent, and for this aim, we are using glutarialdehyde. We used glutarialdehyde in this work. And again, in the presence of a conducting polymer that has NH2 unit, we can directly make a covalent binding between these units of the glutarialdehyde to the polymer. Then when we immobilize the glucose oxidase on the surface of the transducer again, we can have a covalent binded glucose oxidase. So you may ask that how you may show that they are there and they are immobilized. They are not going going from transducer to the system. These may be coming to your mind. And we can say that we are not using any membrane. They are directly immobilized on the surface of the electrode, and this glutarialdehyde cross-linked to the both enzyme and the both polymer. So we can see the repetitive measurements, and we can say that this is repeatable and immobilized enzyme, and we prepared an enzyme-based biosensor. We use this biosensor to detect glucose in the Coke, iced tea, different samples, food samples we applied, and with the good recovery values, we detect glucose. In another example, again, was tyrosinase enzyme. This enzyme is really important for us because I also work in my PhD with this enzyme, and these are the preliminary work actually. And tyrosinase converts catechols to orthoquinones, and in this work we again use covalent binding. I believe that covalent binding makes more stable surfaces than the absorption or entrapment. And again, we use glutaraldehyde, and with the help of these functional units, we can again make an covalent bind to the enzyme. And in this case, we try to find the catechol responses. And again, pH is important for us. We try to optimize the pH values. And in this work, we use magnetic beads. What you are going to use is also important. What you are going to make covalent bind to your enzyme is also important. And with these magnetic beads, you can also take the enzyme binded magnetic beads from the solution with just a magnet, and then clean it, then again put another solution. This is also very useful for us. Now I want to move to the enzyme and drug relationships. How we come up with the enzyme inhibition phenomena. Actually, all the drugs are generated to inhibit an enzymatic mechanism, and therefore they can have their activities. So we have substrate and enzyme. We are making nanobiosensors for this, following the substrate electroactive responses. So when we put the inhibitor to the system, again, our concern was that can we also follow this electrochemically, this inhibition phenomena electrochemically. We are trying to measure the current response before the inhibition. Then we put the enzyme-based biosensor to the drug solution. We waited there, and then again, when we measure, we have seen some decrease in the catechol or decrease in the substrate response. So we may come up with that. We can also use electrochemical enzyme-based biosensor for following inhibition. So you may see here some amperomograms, and after a steady state, we are adding substrate here. And with the bare substrate response, you may see here a big amperomogram. We are just following the decrease in the response here. And after we inhibit the enzyme with different times, different drug concentrations, you can see the decrease in the response. So there's 25% inhibition, we may say like that. So there are different enzyme types, inhibition times, and enzyme and substrate and inhibitor, they can come together, make an enzyme substrate inhibitor complexes. And for in this case, enzyme and the substrate in a race with for the active site actually. So we can say that it's a competitive inhibition. And we have another one. These are the actually that we can follow electrochemically. Of course, there are other inhibition types. And inhibitor directly binds to the not active site but other site of the enzyme and closes the active site of the enzyme. In this case, there is no substrate activity, there is no enzymatic activity, so we cannot have product. So this can be also the non-enzymatic, non-competitive inhibition. So we can follow these two. the irreversible and reversible inhibitions, we can say like that. We can follow these inhibition methods, electrochemical nanobiosensor that we are generating. So why tyrosinase is important for us? Due to the overexpression of the melanin pigment, some dermatological disorders may occur, and this is actually directly related with the tyrosinase enzyme. And if you inhibit the tyrosinase enzyme, you can inhibit the melanin biosynthesis, so there cannot be this kind of disorders in your face. So this is important for cosmetological sector. That's why we mainly focuses on tyrosinase inhibition. And when we search, we saw that metimazole drug can inhibit tyrosinase. And how it inhibits? It can inhibit directly in the first pathway. It can conjugate with orthoquinones and thereby causing an apparent inhibition in the pigment product formation. And we can, if we can follow this electrochemically, it will be very nice for us. So for this idea, first we try to find stable and that we can use also inhibition studies. We try to find a very well a nanobiosensor actually. For that one, we use magnetic nanoparticles. Under the screen printed electrode, we put a magnet, and on the surface of the screen printed electrode, we put magnetic nanoparticles that we again immobilize tyrosinase enzyme, and we try to follow first catechol and orthoquinone conversion, and we try to optimize the biosensing, first biosensing responses. So again, we use amperometric method, and we had a good linear range, and we try to follow them. So when we come to the inhibition, we just try several times, several experiments, how we can show that inhibition. And in the end, we come up that we put a lot of very, very high amount for us, the catechol, and you may see big response. Then when we add metimazole drug, so it can inhibit directly and also indirectly. It can also chelate the tyrosinase, the coppers inside the tyrosinase enzyme, and also it's directly connected to the catechol, as I said. So when we add metimazole, we see a reverse peak, and this was really, really nice for us to follow the inhibition. And in the end, in this case, the inhibitor, the drug, and the catechol is in the same measurement cell. So in the end of injections, different types, different concentrations of drug. When we add 1 millimolar, very high, 4 times higher concentration of the initial one, you may see very little response. It means that during this time, this 1000 second time, tyrosinase is also inhibited by the drug. And when we add catechol responses, it is also connected to the drug, and we can see the both inhibition type of this drug. So we also try to follow this inhibition with the cyclic voltammetry, and you may see here when we add the different concentrations of drug and we take the CV of the catechol, we may see a decrease in the catechol response. Actually, we are following here the minus 0.2 volt, and we are also following at minus 0.2 volt, the catechol response is followed. And this is also, again, proof that this drug can be used in cosmetic sector. They can prepare cream formulation with this drug. It was our suggestion. And also, we try to make this system using Laguna chip system. We prepared small chips for that. Again, put the same nanobiosensor here. In this case, our idea was that if we use very, very small amounts of sample, small amounts of solution, if it is working or not. For this case, again, we put magnet under it, and just 6 microliter volume sample was enough for us. And we can see the detection of catechol here, then the inhibition of methimazole with this very small and beneficial sample. And in another study, this time we try to go one step further, and we try to see if we modify the surface with not the magnet nanoparticles in this case, but iridium oxide nanoparticles. We can take the advantages of metallic nanoparticles, we thought like that, and we use reduced graphene oxide. And for this case, first we electrochemically reduced the graphene oxide, then we added iridium oxide nanoparticles in the system, and again we use here cross-linking method, and we add glutaraldehyde here. And again, after optimizing all the pH, temperature, shelf life, other steps affecting the biosensing response, in this case, we come up with that idea after a lot of searching which drug can inhibit tyrosinase. We come up with that captopril can also be used in cream formulation. There are some works, there are some sentences that saying that captopril also inhibiting. This captopril maybe you may know that it's another usage of drug, and how it inhibits. Again, it can directly chelate the coppers inside the tyrosinase. So first we follow the catechol responses. Then in the presence of catechol, in the presence of captopril drug, there is a decrease in the catechol response, and we follow this inhibition and phenomena with the captopril drug, and suggesting that this angiotensin converting enzyme inhibitor, actually it's another usage, it's another drug usage in the nowadays, but it can also be used in cream formulation for tyrosinase inhibition. Tyrosinase also inhibited by pesticides, so there can be also some environmental aspects, environmental application, and for that we again take the advantages of catechol responses responding first, then using the pesticide in this case, and we can actually, it's like dual biosensor. You can also detect catechol, then also you can detect pesticide in an environmental sample by taking advantage of the inhibition phenomenon in this case. With the again same approach, we add catechol. Then here, when we add inhibitor, we just in this case waited, because generally pesticides inhibits irreversibly, and irreversible inhibition means that you need time to pesticide to inhibit enzyme. It needs time. So after a time, when we add again same amount of catechol, this case, you may say it is not big as like this, so it is inhibited, we may say like that. So with using the same nanobiosensor, you can detect both the substrate and the inhibitor. This was the idea of this work. After that, when we come up with the molecularly imprinted polymers idea with Professor Scheller's group, we say that maybe we can also immobilize enzymes in the molecularly imprinted polymers surface Then we can also again use them in the inhibition phenomena. So I can talk about molecular imperative polymers in short. It's a technology to create selective recognition sites for a target molecule in a polymer matrix. For this case, we are using functional monomers, generally OPD we are using. And what is the idea? We are creating surfaces with the polymer and the analytes, or the what you want. You can also use aptamers, DNA, enzymes. What you want to have imprinted on the surface, you can put the monomer and the, your template. We are saying the template, and together into the solution and starting the polymerization. And in the case of the polymerization, again, same idea with the entrapment method. You have immobilized actually your analyte, your template in the molecularly imprinted polymers, MIPS surface. Then the idea is that you can remove just your analyte. So there are some empty cavities that is specific to your enzyme, or if you are analyzing your enzymes, or what are you going to analyze, you can also prepare specific cavities. And its main advantage is that it's really sensitive compared to other immobilization methods. And in this work, we tried another enzyme, butyrylcholinesterase enzyme. And you may see the polymerization. With the polymerization, we immobilize this enzyme on the surface of the electrode. Then we remove just the enzyme and see that we are following the Ferri-Ferri responses, by the way. We can see that the enzyme is removed, okay? But again, after rebinding of the enzyme, in this case, you can follow not the Ferri-Ferri, but your substrate. Because if the enzyme is there, it will give you an enzymatic activity with your substrate. So it was also good idea from the aspect of molecular imperative MIPS surfaces, and also from our side, enzyme-based biosensors. And for this, we use butyrylcholinesterase, and then we followed 3 different drugs: rivastigmine, neostigmine. These are also using in inhibition of the cholinesterase enzymes, and we try to follow them. And in another work, from the immobilization aspect, I'm using in the generation of enzyme slide I show you, osmium polymers are also used. And in Lund University, Professor Gorton was using these osmium polymers. And in this work, we use pyranose oxidase. This is very comparable to glucose oxidase enzyme. And generally, professors are suggesting not using glucose oxidase. You can use pyranose oxidase for glucose detection. And also there were some engineered enzymes that are genetically modified enzymes for galactose. And we try to immobilize these 2 different enzymes on the surface of graphite electrodes. And with osmium polymers, we just use this osmium polymers as a mediator. And we try to follow the suggested enzyme, and if it is active to do galactose or glucose. So the engineered enzyme is working or not. We are trying to actually prove it is, yes, towards galactose it is prepared. I may say that yes, they just achieve this, but still its response towards glucose is really comparable. So there can be some interference effect in this case from my side. I can try. So we tried many mutants, different mutants and different osmium polymers, and we try to prepare a flow injection analysis for in this work to have much more quick responses directly. And also come up with that there can be some work needed for this preparation. And then actually, as the technology and nanotechnology changes, we just come up with the idea that let's use the graphene quantum dots. You know that Nobel Prize also gone to the quantum dots researchers. So we try to combine the PEDOT, conducting polymer nanoparticles, and graphene quantum dots matrices to immobilize tyrosinase enzyme. And in every work, we are just improving one step the catechol or other substrate responses. And in this case, we just say that let's try other substrate of the catechol also, but nothing responses better than catechol, I may say. So in this work, you may see here screen printed graphene quantum dots PEDOT nanoparticle that enhances the catechol responses. You may see the Bayer just quantum dot, or when we add PEDOT nanoparticles with cyclic voltammetry or with amperometry, we are just first optimizing the nanobiosensing, and then we are try to move to the detection of the inhibition phenomena. And this was the very recent one. Again, we used a synthesized conducting polymer from METU, and we combined them with fullerene in this case. And again, you may see with the CVs and voltammograms, we try to optimize the catechol responses. Then again, we use this for indomethacin detection, and it's also inhibiting tyrosinase enzyme. And the interference effect is important, as I said, in this nanobiosensors. You may see where you add ascorbic acid, uric acid, glucose, other ions, it shouldn't give responses to us in just giving the weak catechol responses. This is important for us. And we are also making the biological method validation of the biosensors with LOD and LOQ detection. And also we are following its shelf life with different days. And I may say what will be in the future of biosensors. You may also know that this biosensor topic is really important because it's also smart biosensors. There are some wearable or tattoos that can follow your glucose level from the tattoos or just from your tears. This biosensor idea is really becoming much more important for us, for human, to detect simultaneously and very quickly, and following the responses of the temperature, glucose concentration, or just miniaturization is important for that, for the wearable biosensor that's also coming. And in conclusion, I just want to make a journey for you with the immobilization platforms that is starting from the Clark. He just come up with the oxygen, oxygen following in a surgery. Then you may see where we came. Now we have tattoos in the, this immobilization phenomenon is really important, as you may use it different times as the enzymes are really expensive and fragile, it gives us really beneficial advantages. So I would like to thank you again, this organization committee and Professor Naveen, for this nice invitation. And you may know this is Turkey's 100th year of Turkey Republic. And I would like to thank Mustafa Kemal Atatürk for giving this chance to us as a woman in science. And I want to say peace at home, peace in the world, with his quotes. And I want to thank you for your attention.
Now the session is open for discussion.
I think everything was clear.
It was a wonderful presentation on how we can develop biosensors with different polymers, and you have made a good attempt in making the different polymers with developing biosensors.
Thank
So
you. Thank you.
yes, that is really good. But on the whole, what is your experience on developing all these biosensors with different polymerization techniques? Uh, which technique is the best one from your experience?
As a person also, I want to be, I want to have quick response and quick idea from the experiment that I'm having. And that's why I generally suggest my student also using amperometry, that we can directly see that enzyme is there. If it is immobilized, it will for sure give response towards substrate by just amperometrically. We may directly see. If it is small, it is okay, no problem. We can increase its response by modifying the nanoparticles. Just I want to see it be immobilized or not. So I'm just always saying to my student also, use amperometry and directly see the enzyme is there because it's a living organism. So if it is immobilized, it will be living there and it's happy to be there. That's why it's converting its substrate to the product. That's, I may say, amperometry.
Yeah, and another question I have regarding the shrinking capacity, shrinking of this structure of these enzymes can happen when we are developing these polymers. So how, what kind of polymer, like materials, or is it a covalent or a non-covalent hybrid bonding you can suggest on that?
Actually, it should have some functional groups like NH2 units that we should have covalent binding, that should have NH2 or carboxyl groups. It is a reason of choice actually, that we can have covalent binding to the glutaraldehyde or other covalent agents we have. And if not, we can use, in this case, we can change the methodology to entrapment. We can prepare while polymerization, we can add the enzyme, and then we can make an entrapment. We can change our strategy depending on the polymer. And if it is still not working, we can add carbon nanotubes or fullerene, other very well conductive agents. If it is still not working, we can add inside to the enzyme the metallic nanoparticles. We may add, then immobilize the enzyme. So depending on the nanoparticle, nanomaterial, or the immobilizing substrate, we can change the immobilization strategy easily.
How about the rigidity of the polymers when you are immobilizing?
How? Sorry?
A rigidity of the polymer with respect to the immobilization of your enzyme.
Yeah, they should be rigid. They should be stable for sure. That's why maybe we are using conducting polymers generally, and they should also be after polymerization. They should be also be stable for us. We are directly using sometimes directly polymers, not monomers. But generally, to have rigid ones, we are starting from monomer, and also optimizing the polymerization conditions depending on the enzyme or the drug molecular weight. We are also making a rigid and stable surfaces.
Thank you, ma'am, for your nice presentation. Ma'am, I have one doubt. In one slide, you have mentioned about osmium polymer membranes and the enzyme immobilization. So can you please mention the significance of that osmium polymer membrane in the enzyme immobilization process and how you have prepared that membrane?
In that case, we used dialysis membrane. They are just on the we are using him, and we are putting the osmium polymer that was synthesized, and when we add the enzyme, the electrons from enzyme coming to the osmium polymer, then it is coming to the electrode surface. So every osmium polymer has also its own electrochemical state, and then we may follow them, and not the enzyme to drop from the electrode surface. We may also put dialysis membrane on the surface of the electrode, on the surface of the transducer. Then you may also make an enzymatic biosensor. There are also different kinds of polymers like that, osmium polymer, but it is the well-known, mostly used one in mediators. There are some also like ruthenium or iron-based one, others also used in that case.
Okay, ma'am. Ma'am, what about the stability of this immobilized electrodes? Whether you're preparing a disposable electrode or we can use this electrode for a long time?
That's why we are making shelf life measurements. So we are preparing the biosensor, taking the response, suppose towards catechol. Then we are measuring it in the first day, and then we are putting the biosensor to the fridge. And next day we are coming and again measuring it. And we can do this depending on the biosensor type, but 20 days is the limit for me. 20 days, if I can use it for 20 days, it's okay for me, for the teacher also. But just also we are making in-day repeatability, following it with operational stability and shelf life. Two stability experiments we are doing, but the technology is going like that. Just you are measuring your glucose level from your blood, and you are just measuring it and throwing the biosensor. So just one time you are using that biosensor. So there is a problem for the waste. You are losing, but you don't want to use that something had blood already in it. So there are some also physiological problems, environmental problems, psychological problems. So that's why actually the technology changing to the wearable sensor. So when you have a stick here or tap here, it can always following your glucose level here, and without any blood, without anything, it is just here. So for this case, it should be stable for many times, maybe 6. If you are making a tattoo, it will stay there. But there are also some experiments that are making every month, if it is giving still the same response from the beginning of the day. But for in our cases, we are using electrodes, glycocarbon or graphite or superprinted electrodes, and we are following their responses for 30 days, for 1 month, always.
Thank you, ma'am.
If you leave me, I can talk a lot. Sorry.
Hello, ma'am. Ma'am, can you please explain the influence of the other isomers of catechol, such as resorcinol? What will be their effect?
Catechol is the substrate, well-known substrate of the tyrosinase enzyme.
No, ma'am. I'm asking about the influence of other isomers of catechol.
Other isomers of
Yes.
catechol.
Resorcinol. Yeah, influence of that.
Yeah, for this case, it depends on your matrix actually, because we are using pure catechol. But this is another work is ongoing in our study now. If you have total phenolic analyte that is also like resinol or other phenols, also substrate of the tyrosinase, you may come up with the total phenolic compound response, not specifically with the catechol, because tyrosinase is converting the OH units on the catechol, and it has nearly all phenols have these OH units. It converts to double bond oxygen. So we cannot specifically detect this is from catechol, this is from resinol. We cannot just say that. We can say total phenolic compound of phenolic content of the sample, we may say like that.
Okay, ma'am. Ma'am, one more query. Can you please elaborate the stability of these enzyme-based catechol sensors compared to non-enzymatic sensors, stability-wise?
With the non-enzymatic ones or not immobilized enzyme-based ones?
Okay.
Which one you want to be compared?
No, that immobilized and there won't be any enzyme. It means conventional sensors, no? Without enzyme.
Yeah, you should, yeah, when we immobilize the enzyme, yes, we are having immobilization of the enzyme. We can take the enzyme from the solution.
Dr. Savage, I think she's asking you, like, compared to the conventional electrochemical sensors we have,
Dimensional.
biosensors, yeah. So considering that you are using enzymes which are biomolecules, which may not be having a higher stability, the duration, the durability of this biosensor you make. So how do you compare? That's what she wanted to.
With the enzyme-based and non-enzymatic ones, you want me to compare their stability?
Yes, the enzymatic biosensors with the non-enzymatic biosensors.
Yeah, in the non-enzymatic biosensors, it means actual nanosensors that we can follow the like dopamine and follow their responses. Of course, non-enzymatic ones much more stable with enzymatic ones, and that's why actually some of my collaborators are also try to synthesize nanomaterials that can behave like enzyme, but we are not immobilizing enzyme. We are just putting the nanomaterial. Again, we can have much more responses supposed towards catechol, but there is no enzyme, just the catechol response we are following. Of course, if you don't have any biological material, not enzyme, not DNA, not nothing, but still you can follow the substrate of the enzyme, but there is no enzyme, it is much, much more stable, of course. I hope I understand and you get the response.
It's clear. Are there any questions?
Hello, ma'am. Just really informative talk. So I have one query that is in enzymatic reaction. So we can monitor the current based on either the byproduct or the enzyme that is undergoing oxidation or reduction at the electrode surface, or the redox marker we can use. So which one actually gives more reliable results? That whether it depends on the byproduct oxidation or reduction or a redox marker we are using.
If your substrate is electroactive, I may suggest you to use the substrate itself, or the product is electroactive, you may directly use. But if it is not like that, you may use the redox marker like ferro, and you can also use other methods like impedimmetry, or you can just follow the resistance on the surface. As you add biological material or your substrate, the impedance levels are also changing. But if nothing is electroactive, you need to follow the change in the surface, what is changing in the surface, you should follow it. In this case, you should use redox markers.
Okay, ma'am, thank you.
You are most welcome.
Any more questions? Thank you, ma'am, for your enlightening talk. Your knowledge and perceptions were incredibly motivating. On behalf of Department of Chemistry and the entire Amrita family, I extend my heartiest gratitude for you to joining us.
I'm very thankful to you, to all, for this nice invitation and for nice discussion. And you are the most welcome. I hope in some days we can meet face to face.
Yes, thank you, ma'am.
So, with this, we have come to the end of today's keynote session. I'm delighted to inform you that the oral presentation by our esteemed participants will continue today also. Today, we'll be having oral presentations in two streams. Stream 4, Environmental Sciences in Shraddha Hall, and Stream 5, Electrochemical and Theoretical Chemistry in Amba Hall. So, prior to that, we'll have a short tea break.
ഫോൺ കണക്ട് ചെയ്ത് ഞാനൊന്ന് ചെയ്തോ നോക്കട്ടെ. എനിക്ക് ഇത് ഓഫ് കേബിൾ കണക്ട് ചെയ്തൊന്ന് ചെയ്ത്.
അവിടെ ഒരു ഓളം ഇത്
പൊങ്കലായിലോ പാടും പാടും നീ ആദ്യം മുതലൊന്നും ഓക്സിജൻ ഒന്ന് ഫിക്സ് ചെയ്ത് തരാമോ? ചാവും. കഞ്ഞി ഒന്ന് പാടിയോ നീ?